change, right? When the volume of this one increase, this one decrease. I can pour them back to check. Let's see our marker here. Can you see? Yeah, it's the same. So one increase, the other decrease, and vice versa. But the total amount doesn't change. This is the idea of conservation. Now Frank is going to explain the conservation of angular momentum.
So when we make something spin, it has a property we call angular momentum. And angular momentum is a combination of two things. It's a combination of rotational inertia, which we've been talking about, and how fast it's spinning. And once an object is isolated, that quantity, angular momentum, can't change. It is a conserved quantity. It's a constant. It doesn't change. So if we can magically decrease the rotational inertia, then the speed has to increase. Let's see what that means in practice. I'm going to use a Hoberman sphere to demonstrate that. Maybe you have one of these at home. You can get them in most toy stores. I can make it bigger. I can make it smaller. When I make it bigger, the rotational inertia is big, right? Because the stuff is located far away from the center. When I make it smaller, the rotational inertia is small. So now I'm going to spin it and give it some angular momentum. And now if I make it smaller, it has to spin faster. And if I make it bigger, it has to spin slower because the angular momentum is the same. The combination of the inertia and how fast it's spinning is a constant. Okay? Jan Rue is going to tell you a little bit about where you might see this next month in the Olympics.
Who's going to watch the Winter Olympics this next month? Are you excited about ice skating? I like ice skater. David will be our ice skater today. I will spin him. Okay. When he pulls his arms in, his speed will goes up because his angular momentum goes down. When he stretches out his arm, his speed goes down because his angular momentum increases. Rotational inertia increase. So the combination of the speed and the rotational inertia keeps the same. Can you help?
Lucky for us, David is a Renaissance man. Not only is he an ice skater, he's a helicopter. Wait a minute. Something is wrong with this helicopter. What's missing? The tail rotor. So when that big propeller turns in one direction, the helicopter, just like David did, would spin in the opposite direction. And so we have that propeller pushing sideways, preventing the helicopter from spinning around. Or it could have two big propellers that spin in opposite directions. That would work also. But angular momentum conservation is something we see all around us. Now, what we've been talking about so far is the amount of angular momentum has to stay the same. If it's 5, it's going to stay 5. If it's 142, it's going to stay 142. But angular momentum is a special kind of quantity. It has a direction associated with it also. So if I give this wheel a spin and give it some angular momentum, you might say it's turning counterclockwise. But that gets kind of confusing, so we say that the angular momentum points toward you. And if I spin it in the opposite direction, the angular momentum points toward me. And so the direction of the angular momentum also wants to stay constant. Jan Rue, maybe the kids have played with a toy, and you can explain how that works?
Okay, let's look at this bike wheel. Okay, so if I just put it on the ground, do you think it will stand? No, it fall over. What if I spin it first and then put it on the ground? It stands up. Why did it stand up? The bike will stand up because the direction of its angular momentum wants to stay up. When the gravity tries to pull it down, the angular momentum wants to stay up, so the direction doesn't change.
This next one's my favorite. I'm going to put Frank on this platform, then he's going to flip that bicycle wheel over. What? Do it again, Frank. One more time, Frank. I could watch this all day long.
Make it stop.
What's going on here? It turns out it's the same thing we've been talking about. This is just more angular momentum. So Frank started that wheel spinning. It had angular momentum pointing upwards. He had zero angular momentum. He was not spinning at all. Then what happened is he flipped that wheel upside down. The angular momentum of the wheel was pointed towards the ground, but Mother Nature wants to conserve angular momentum. If it started pointing up, it has to end pointing up. Mother Nature noticed that Frank was standing on a rotating platform, so Mother Nature started rotating Frank.
We've been talking about angular momentum and rotational inertia. Let's do a quick summary. Rotational inertia. Where else might we see this? Well, maybe you've noticed this yourself. You're standing waiting to cross the street. A light turns green. A car starts up to go across the street. And what does the front of the car do? It lifts up a little bit, right? As the car goes forward. Conservation of angular momentum. The wheels turn one way, the car has to turn the other way. That's not a problem for our cars, right? The wheels aren't that big, the motors aren't that strong. But what if you had a drag racer with huge wheels and big, strong motors? When those wheels turn one way, you don't want the car to flip upside down, do you? So you make the front really long. And that way you can put a small weight at the front and really increase its rotational inertia so it doesn't flip over. We talked about ice skaters. The same is true with the high divers. They go off those high platforms in the Summer Olympics. The announcer tells me they spin around 3.5 times. I believe them. Then they kick out, and it slows their rate of rotation down because their rotational inertia goes up, and the speed has to go down, and they can go into the water without making a splash. We talked about the top. But the same is true of other things in sports. Projectiles like footballs, if you give them a nice spiral, they go nice and straight because the direction of the angular momentum wants to stay constant. And my sons play a lot of hockey. When they pass that hockey puck, if they just slap at it and don't give it spin, the puck sails through the air. And when it hits the ice again, it bounces and flips and rolls, and their teammate has a real hard time doing anything productive with it. But if they spin that puck as they pass it, it goes through the air and it hits the ice and it stays flat. And it doesn't roll and it doesn't bounce, and their teammate can grab it and do something with it. So you never know when your knowledge of physics will come in handy. On an airplane, satellites, airplanes, they have gyroscopes in them to help them know what direction they're pointed. Let me show you how that works. I have a gyroscope here, and it's on a gimbal, so it can turn in all different directions. And mine is not bad. It has pretty low friction here. It's not great. The ones in airplanes and satellites are much, much better. But I'm going to get it spinning. You are getting sleepy. I know what my students would say. They'd say, Professor, you don't need that to put us to sleep. Okay, so the angular momentum is pointed toward the camera, and the airplane takes off. Up, 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 up it goes. It levels out. It turns this way. It turns that way. What direction did this point the whole time? Right at the camera, right? It never moved. And that's the idea with these gyroscopes. Once they get oriented, they never want to change direction. The airplane, the satellite moves all around, and it always knows its orientation relative to the gyroscope because the gyroscope doesn't change. The physics of angular momentum, it's all around us. And that brings us to our next topic, torque. So why did the wagon start to move earlier? Because we exerted a force on it. A force caused something to move. Why does something rotate? Because of a torque. It's a little bit more complicated than just exerting a force. It matters where we exert the force on the object. So if I wanted to make this gray object rotate, and I pushed over here, is it ever going to rotate? No. If I push over here, I might get it to rotate, but it would take a big force. And if I pushed out here, that's where it requires the smallest force to get it to rotate. But maybe the easiest thing is just let's pick an example that we're all familiar with, right? How about walking through a door? Let's take a look at that example. And since we're in a theater, we have a door handy. The side closest to me, that's where the hinges are. We call that the axis of rotation. That's where it's spinning, about that side. And the other side is where the handle is, and that's going to open and close. And if I was in a hurry to get through this door, and I pushed over here, am I ever going to get out? No. And if I move my hand over a little bit, then I could get the door to open, but I have to put a really big force. And if I move over a little bit more, I could get the door to open with a smaller force. And if I push on the doorknob, I could push with the smallest force to get the door to open. That's why we put the doorknob over there. And so you can try that at home, push on different parts of the door, and see how it's easier when you push far away from the hinges to get it to spin open, to rotate, than it is when you push close. And that's the idea with torque. It's a combination of the force and the distance. So I have here as a meter stick. It's reasonably well balanced. The mass on one side is pulling down on that side, creating torque, wanting it to spin in that direction. And the mass on the other side is creating torque, wanting it to spin in this direction. And if I push right at the axis of rotation, I can't get it to spin, right? Even though I'm pushing with the hard force. And if I push over here, I can get it to spin and rotate. And if I push way out here, it takes an even smaller force to get it to rotate. Okay, that's the idea with torque. The further away you are from the axis where it's spinning, the less force is required to produce the same torque. Now, if I put a weight over here, I have a force, I have some distance, so I'm getting torque in this direction, and if I let go, it rotates in that direction until the weight hits the table over there. Now, if I put a bigger weight on this side, I have a bigger force at the same distance, so this is providing more torque, and it's going to win. And the whole thing's going to rotate in that direction. But I want to balance it. I've got a small weight and a big weight, but I want it to be balanced. So I have to move the small weight out far away, so I have a small force and a big distance, and the small force and the big distance is going to be the same as a big force and a small distance. And if I let go of it now, I can leave it balanced. And since we're talking about balancing things, David is going to tell us what center of mass is.
So you say, what's center of mass? Well, I like to think of center of mass as being the balancing point where if you hold something by the center of the mass, the torque on one side will exactly balance out the torque on the other side. So you take something simple like a stick, and you say, well, where do you think the center of mass of our stick should be? Yeah, about the middle. So you can probably guess where the middle is. You can put your finger right there. And, well, sometimes you just drop it. But sometimes it just doesn't balance very well. But we say, well, it should be about the middle. I've got a trick. I'm going to put one finger on one side, the other finger on the other side. I'm going to start moving them in. And when one finger supports more than the other does, it's going to have more friction, which will cause the other finger to slide. And there'll be this little balancing game where one will slide, the other will slide, and they'll keep sliding until you get to the center of mass. So if I support it right there, both sides balance. Now you say, that's nice and easy for a stick. Can you do things more complicated than a stick? Look at this. It's got a big wooden thing on one end. It's got a dense metal thing on the other end. I'm not really sure, just looking at this, where I think the center of mass should be. But I'm going to do my trick again. I'm going to move my fingers in. You can try this at home with a ruler or a broom or whatever you want. You just bring it on in and you can say, well, I can balance it right there. So you can put your finger right there and the torques balance. Now, this is what happens when you're supporting an object from underneath the center of mass. The center of mass does the other things with objects. What you can do is you can hang an object. Frank, do we have any fun shapes?
Is a triangle a fun shape?
A triangle is totally a fun shape. So we're going to hang a triangle off of this support. Hang it by a corner there, Frank. Then we're going to take a piece of string with a weight on it. And that piece of string is going to point right down towards the center of Earth. And what we know is that the center of mass has to be directly underneath the support point. So somewhere on that string line is going to be the center of mass. Now we can hang it by another part of the triangle. And we'll do the same deal. We'll hang the string down. And the center of mass has to be somewhere along that string line because the center of mass is going to be directly below the support point. One more time because it's a triangle. And we cheated. Before the physics show, we got some permanent marker. We marked where all these lines were. And where all of these lines meet, that has to be where the center of mass is. So now Frank is going to balance a triangle on his finger. Now you look at that and you say, well, wait a minute. Triangles are kind of straightforward. You could probably eyeball a triangle.